right, so 2.09, what we'll be looking at is optimization, and we'll do several examples together on that. So in optimization, what you're trying to do is you're trying to find a maximum or a minimum. And on the first page, this is more of an outline of the steps we're going to go through to solve the problem. So you don't have to write anything on page one. We're going to be kind of going through the steps and the different examples I'm going to go through today anyway. So optimization are problems where you're looking for a maximum or a minimum. So let's go to page 2, and then we'll kind of start this, and then we're going to kind of talk about the steps you go through on these. Okay, so the first problem, example 1, is a real basic one. So what this says is it says you're going to find two numbers that have a difference that's 100, and the product's a minimum. Okay, so it has that word minimum in it, so that's what makes it an optimization problem. Okay, so what we're going to do is just kind of randomly come up with two numbers that you would subtract and get 100 out of. Give me two numbers you would subtract and the result would be 100. 101 minus 1. Okay, all right, so that difference would be 100. The product would be 1 times 1 would be 101. Okay, give me another one. 110 minus 10, okay. All right, so that would have a difference of 100, and now you'd have 10 times 110 would be 1100, okay, like that. Well, usually students don't think about negative numbers. Here's another possibility. If we had like negative 100 and negative 200. If you did that, if you subtracted negative 100 minus a negative 200, you would get negative 100 plus 200. So that would still give you a difference of 100. Okay, yeah. Well, I did 101 minus 1 has a difference of 100, and then the product would be 101 times 1. So, I see right there. Yeah, I have the product right. Okay, so now on this one, if I multiply these two numbers here, I get a 2 and then 4 zeros, like that. Okay, so the idea is somewhere in here is a minimum. Okay, right now the minimum product is 101. Whether that's the answer to the problem or not, we don't know. We're going to figure that out. But the idea is the conditions of the problem are saying two numbers, subtract to give 100, and they multiply to give some number. We're looking for the two numbers that minimize the product. Okay, so down in step 2, first of all, our variables are just going to be x is equal to the first number, and then we'll let y be the second number on that. Okay, so we want to get that. Okay, what we're optimizing is we're optimizing the product. So we're finding the minimum product on that. So that's what we're optimizing. Okay, the objective function is always what you're going to take a derivative of. Okay, so how do you take the product of x and y? How do you write the product of x and y? xy, exactly. Okay, so that is your objective function. Now I'm going to write a notational system that you're not familiar with. We say f of xy. Okay, now what I'm going to do on that, you could say f if you want to. I'm going to just use p of xy to stand for product. You don't have to do that, but I'm going to do that then. Okay, so now what happens on there is you have to reduce this to one variable. The objective function, which is the product of x and y, has two variables. So there is a secondary equation. So let me ask this question. How do you write in algebra that x and y have a difference of 100? How do you write the difference of x and y? What does difference tell you to do? Subtract, okay, so that's going to be x minus y equals 100. Okay, that's what we call a secondary equation. Now, what you have to do to get the objective function to one variable, you have to take that secondary equation and you have to solve it for either variable. It's up to you which variable you solve it for. I'm going to choose to solve it for y, so I'm going to choose to move the y to the right side and the 100 to the other side, so I'd have x minus 100 is equal to y. Okay? Now what happens, and this is the whole key to these problems, is that's what y is, so what you do is you just take that and plug that in. Okay, so what you're going to get now is you're going to no longer have xy, you're going to have x times x minus 100, and then now that's a function with one variable, so I just write that as p of x equals x times x minus 100. Okay, like that. Okay, does that make sense what I did? That's the whole key to the problem right there. Is everybody okay? Okay. All right, so now I have p of x equals x to the second minus 100x, okay, and that's a real big deal right there. This is our objective function, okay? There's actually a couple of things that I'm going to highlight that are real important in the problem. There's that, and then there's this equation y equals x minus 100. So the first part of the problem is setting everything up. The rest of it is things we've been doing in class, and you've done homework on this, so you probably do fine from here. So constraints, there are none on this problem, and that's because x and y can be any number. That won't always be the case. It depends on the situation. Okay, so now if we go to step 5, you want to write down the objective function, which is x squared minus 100x. All right, now it says find critical numbers. Okay, hopefully you guys know that by now. How do you find critical numbers? You take the derivative, set it to 0. So go ahead and do that. Don't wait on me. You can go ahead and do your derivative. So what's your derivative? 2x minus 100. Okay. Go ahead and set that equal to 0. Or I'm sorry, take 2x minus 100 equals 0. Now you want to go ahead and solve that equation, okay? And you can add 100 to both sides. You're going to get 2x equals 100. Divide by 2, so you're going to get one critical number is x equals 50. That is your only critical number in that problem, okay? Okay, so we got that. Now we're going to make a sign chart. So when we make our sign chart, the purpose of the sign chart is to kind of see if this is a minimum or it's a maximum. We're trying to find a minimum on this. Okay, so on a sign chart, what do? We plug numbers in less than 50. I'm going to use 0, and I plug that into my derivative. So my derivative is 2x minus 100. So if I just do 2 times 0 minus 100, that gives a negative number. So is my function increasing or decreasing? Increase or decrease? Negative derivative. What does that tell you? Decrease. Okay, good. Okay. Now we're going to take a test point bigger than 50, like 51, and then we plug 51 into the derivative. So we do 2 times 51 minus 100, and that will give a positive, so that tells me we increase. Okay, so based on that sign chart, is 50 a minimum? If the graph decreases, then increases, is that a minimum? Yeah, okay. So the sign chart proves that that's a minimum. So 50 is going to end up being the minimum on that. Okay. All right. Now what we're going to do is we're going to go ahead and check this graphically. So what I want you to do on this is do this on your calculator. We're going to graph the objective function. Okay, so let me tell you what to put in here. So go ahead and do this on your calculator. So the objective function is x squared minus 100x Okay, set up the window that I have over here. You'll see a window that I have displayed here. So what we're going to do here is go, for X minimum, we'll go 0, X max will go 100. I'm doing that because 50 was the critical number, so I want 50 to be in the middle of that somewhere. Then I can scale by 10. And as far as the Y's, you'll see this well if you do negative 3,000 for your minimum, and then you'll see 3,000 for your maximum, like that. So you want to get that set up, and I'm going to write down, and you should write down on your notes what you are graphing just for reference. Okay, so we're graphing the objective function x squared minus 100x, and x minimum was going 0 to 100 by a scale of 10. Y minimum was negative 3,000, Y max was 3,000 by a scale of 1,000, like that. Okay, now once you get that set up, this is what your graph looks like. So I'm going to have you just kind of sketch a graph on this, a very rough graph of this, and then we'll kind of put together the answer to the problem. Okay, so again on this, you don't have to have all of this. We're just going 0 to 100. 50 was where the minimum was. And then let's just do like 3,000 and negative 3,000, like that, and just get a few points from our graph. Okay, so what I'm going to do is trace on this graph. If I trace it 0, I get a point 0, 0. If I trace at 50, which is where our minimum is, you can, first of all, you can tell that's a minimum by looking, and then that is a point 50 and negative 2,500. And then you've got this other point you can tell pretty well by looking. You have the point 100, 0, and then you can sketch in the graph like that. Okay, so the purpose of using your graphing calculator is to verify that the minimum is correct. Okay, any questions about what I did on the graphing calculator? What's most important on this is you graph the objective function. It's the objective function is what we did the derivative of. That's what you're trying to verify. Okay, so now we'll just state the answer. So there's a couple of things we have to do. X equals 50 is the first number. And then if you go back earlier in the problem, we had y equals x minus 100. Remember the difference of this. You ended up having x minus y was equal to 100. So we also have to find y in this problem. So we have 50 minus y equals 100. Then we can solve this equation. So you would just kind of rearrange this. I'm going to move the 100 to the left side. I'm going to move the y to the right side. So I end up getting y equals negative 50. Okay, so those are the two numbers right there, are 50 and negative 50. So your answer to this problem is just going to be the two numbers are 50 and negative 50. Okay, now let me just show you a couple of things on this. If you do the difference of these numbers, if you subtract these two numbers, that's 100, right? Okay, which it was supposed to be, but if you multiply these two numbers, you get the minimum product, which is negative 2,500. So when we did that kind of chart at the beginning of the problem, nobody thought about 50 and negative 50. Okay, there's no way to really figure the problem out with a chart unless you tried every single number possible, and you're not going to do that, obviously. Okay, that's the answer to the problem. Is there any question on what I did there? Okay, are we all right? I don't have a clue. I'm all right. Are you all right? Okay. Now, all of these problems are going to follow this same kind of strategy. They get a little bit harder, maybe. They all have kind of different ideas in them. This example 2, if you read the problem on example 2, it's going to say that you're finding dimensions of a rectangle that have an area that's 1,000, so that's something you're given in the problem. And then it says the perimeter is as small as possible. So what you're doing is you're finding a minimum again in this problem, okay? All right, so what I'm trying to show you with these different rectangles is you could do all kinds of different rectangles. Like you could do one that was real long and skinny, and you could have something like that could be 1 meter by 1,000 meters, and that would have an area of 1 times 1,000, which would be 1,000 meters squared. That's one possible answer, but that rectangle has a very big perimeter, right? Okay, it's a very, very long perimeter. Perimeter is the distance around the rectangle. Another possibility would be something like this. 10 meters by 100 meters, again, would have an area of 10 times 100, so it would have an area of 1,000 square meters. So I'm just trying to show you there's all kinds of ways to write a rectangle, but with an area of 1,000, but there's only one way to minimize it. So that's what we're going to look at. Okay, so in this next step, the variables are going to be, we're going to go ahead and just draw a picture of a rectangle. So just draw a rectangle and decide what your variables are. So what I'm going to choose to do is x is going to be those sides, and then y is going to be those sides. Okay, so we have two different variables in the problem on that. So we're going to say x is the height, and we're going to say y is equal to the width. Okay, so that's what we have. Okay, all right. So that's the situation. So what does it say we're optimizing? What are we trying to make as small as possible? You got a phone going on up there? Get your phone away, please. Are you writing any notes today? Okay, well, put your phone away. I can tell when you're on your phone because you're looking down, you know. Come on. Okay, what is it that we're trying to optimize? What does the problem say? Okay, the perimeter. Okay, good. So we're optimizing the perimeter. Okay, and that's going to be a minimum. Okay. All right, so let me ask you a question. Perimeter is all the sides added up. So what do you get if you add up all these sides in terms of x and y? X plus y is what? 2x plus 2y, right? Okay. So that would be a perimeter, and that would be in terms of two variables. Okay, so perimeter just means add up all the sides. Okay. So now the question is there a secondary equation? Okay, let's see if there is one. How do you find the area of this rectangle that I drew? X times y, thank you. So that is x times y equals 1,000, so you want to write that down. Okay, so the whole purpose of this is we got to get this objective function down to one variable. So what you're going to do is you're going to take this equation, x times y equals 1,000. You have to solve it for either variable. I almost always solve for y, but you don't have to. So I'm going to divide both sides by x so that I get y is equal to 1,000 over x like that. Okay, now what you're going to do with this is that plugs in for y right there. So you need to plug that value in right there. Okay, and then we're going to have an objective function that's going to have one variable. So what we're going to have is 2x stays the same. Now we're going to have 2 times 1,000 over x like that, and now we've got that down to one variable. So I'm just going to say we're perimeter of x like that. Okay. Now I'm going to write this in one other way because in the next step of the problem we're going to have to take a derivative anyway. So I'm going to write this as 2x plus 2,000 x to the negative 1 like that. Okay. So that's the objective function. Now it's important, like when you get your objective function with one variable, it's important when you're doing work that you highlight it or something, because this is what you're going to graph. This is what you're going to do your critical values on. You're always going to graph that objective function to see if you're doing the problem right or not. Okay, so step 3 is the key to the problem. If you can get the correct objective function, the chances of you getting this right are pretty high, because now it's derivative and critical numbers, and the derivatives on all these problems are not going to be hard. Okay, any questions so far? Okay, all right. So now, constraints in the problem. Yes, there are constraints on this. So the idea is, with this, you're going to kind of find that at the very smallest, your side could be, you couldn't have a side of 0, but you can get close to 0. Okay, and then the biggest side that you could possibly have might be like 1,000. Okay, and the purpose of the constraints is to kind of help you understand how to, use your window when you graph and that kind of thing like this. So if you had 1 times 1,000, you would have an area like that. Now that 1 could be smaller. It could be like a decimal or something. Okay, so the idea on this is, what I'm going to really just say on this is, your length has to be on this interval. The length has to be on the interval 0 to 1,000. Okay, because if it's bigger than 1,000, you're not going to be able to make a correct rectangle or anything. So that's kind of an idea. Okay, so now we're going to do the critical numbers. Okay, so again, what do you do to find a critical number? Take the derivative and set it equal to 0. So you need to do this derivative. What's the derivative of this function? 2x. What's the derivative of 2x? 2. What's the derivative of 2,000x to the negative 1? Minus 2,000 x to the negative 2, right? Okay, so that's your derivative. I would go ahead and write this as 2 minus 2,000 over x squared, and then that's what we're going to set equal to 0. Okay, so these are things that we've been working on this for quite a while now. Okay, so we've got 0 equals 2 minus 2,000 over x squared. Okay, there's a couple of ways to do this. One way to do this is to multiply both sides by x squared to get rid of the fraction. Okay, that's general ideas. If you got an equation with a fraction, get rid of it. So what you're going to have is the left side is 0. I'll just kind of move this over here. So I've got 0 equals, and then you got to distribute that to get 2x squared, and then you can cancel that out to get minus 2,000 like that. Okay, now what you're going to do here is isolate x squared, so we can add 2,000 to both sides. Okay, that will give 2,000 equals 2x squared. Then we can divide by 2. So that gives x squared equals 1,000. And then what we need to do is take the square root of both sides, and then we'll just use our calculator to get an approximate answer on this problem. Okay, so we're just going to work out the square root of 1,000, and then we'll have to see if the sign chart will tell us if that's a minimum or not. So on a blank screen, okay, I'll go ahead and do that. So I've got square root of 1,000. Okay, that's going to give about, let's round that to 2 decimals. That's about 31.62 is about what x is then. Okay, so that's our critical number right there. Okay, now what we're going to need to do here, what's that? You technically, negative 31.62, because you're used to doing plus or minus, doesn't make any sense in the context of the problem, because a rectangle is not going to have negative sides. Okay, so that's why I did that. Okay, so now what I'm going to do is we're going to make a sign chart. Okay, so we do this, and we got 31.62. And we don't need to worry about anything below 0, of course, because this is sides of a rectangle. Okay, So again, sign chart, pick a number between 0 and 31.62, and where do you plug that in? Derivative, okay. All right. Remember, when you're doing a sign chart, you're testing the first derivative. So I highlighted the first derivative in yellow. So you do 2 minus 2,000 over 1 to the second. That's a negative. So am I decreasing or increasing? Decreasing. Okay, that's what we're kind of hoping will happen. Okay, now pick a number bigger than this. Okay, like I'll go with 100. It doesn't matter what you use, but as long as it's bigger. So I'll do 2 minus 2,000 over 100 to the second. And you could do that on your calculator. You will get a positive when you do that. So that means the function is increasing. Okay, does that sign chart prove that that's a minimum to you? Yeah, what's the function doing? It's decreasing, it's a low point, and then starts increasing. So that is a minimum based on our sign chart. Okay, that's the idea. Okay? All right, any questions on that? Now we're going to graph some of these. I'm not going to do all of the graphs on here, but sometimes students get a little confused about what you're graphing, and what you're always graphing is the objective function. So just do this on your calculator with me, and we'll do a graph on this one and maybe one other one here in a minute too. So put in the objective function, which is 2x plus 2,000 times x. Whoops. Okay, so then we'll have x to the negative 1, like that. Okay, and for a window, what we're going to do on a window is, first of all, 31.62 was the minimum. So I'm going to maybe just leave this at 100. And then for the y values, you need to look at your table of values. So if you kind of look at the table on this, what you're going to find on this is when x is 1, I've got 2,000 approximately. The numbers are going to get smaller. Eventually, they're going to start getting bigger. And if you go all the way on around that 31, what's going to happen when you get around 31, you're going to see that this thing starts getting bigger again. So what I'm going to do on my window is I'm going to go 0 to, let's do something like maybe 2,000, maybe by a scale of 500 like that. Okay, and then I'll just put in a graph. So again, what we did is we graphed the objective function. Then we get a graph that looks like that. Okay, does that graph look like it has a minimum? Yeah, okay. Our minimum was 31.62. So I'm going to trace 31.62 and just kind of visually see if that's a minimum, okay? And you can pretty well tell that looks like that's a good minimum right there, okay? So really all I want you to kind of do on this is just make a very rough sketch of this graph. You've got 100 there. I think this was 2,000. And then just label that point as 31.62 and 126.5 approximately like that. So what we again graphed is we graphed 2x plus 2,000, x to the negative 1. The window was 0 to 100 for x. And then we did 0 to 1,000, or no, to 2,000 on that. So now what we're ready to do is kind of put together our answer, and we've got to write that correctly then, okay? Say that again. Oh, on my window? Yeah, on my window is, what I did was this. Yeah, I scaled by 500, okay? So you just want to have a good enough window that you can visually see whether that's a minimum or not. Okay, so down in step 8, just draw yourself a rectangle. What we found was x was 31.62. And in the problem, that was, when we set this up, that was the height. So we still have to find what y is, because we're supposed to find the dimensions. Okay, so here's kind of what you could do on this then. The original problem, we had 2x plus 2y equals, and that was, no, let's see, we had x times y is 1,000. So we had the equation, we were given that the area was equal to 1,000. So now what you do is just plug in that x value. So you would have 31.62 times y equals 1,000. Then we can divide by 31.62. And then that will give the other dimension on this then. Okay, so we just do that on the calculator, and that will solve the problem for us then. Okay, so we just do 1,000 divided by 31.62, and that'll give the same thing. It'll give 31.62. So what we find on this problem is the dimensions of the rectangle, it's really going to be a square. So it's 31.2, I can't remember in this problem if it was inches. No, it was meters. Okay, so it's 31.62 meters by 31.62 meters, like that. Okay, so that's the answer to the problem. What you end up finding basically is you turn this thing into a square. That's how to minimize the distance around. Okay, all right, so if you think about that, to me, that's pretty logical. If you have a rectangle, if you want to make the distance around it a minimum, you kind of compress it to a square. Is that logical to you? You could have done it that easy. You could have. But how would you know that? You know it now. And this will only work if you're doing just a rectangle. So like if I change the problem to it has an area of 500, then what you would do is take the square root of 500 and you would have your minimum just like that. Okay. Every situation's a little bit different, but certainly on this problem, that's all you would have to do to get that answer. All right. All right, let's go into example 3, then we'll take a break here. This one is a little different twist. Okay, so on this one, what we're going to have is the only difference with this problem is it says you have a 3-sided fence. It's built next to a section of river, and it's going to form a rectangular region. And this problem, you're given this information, that there's 96 feet of fence available. And then the question is, find the maximum area. So when we draw a picture on this one, it's going to be a little bit different this time. What you're going to have is that's kind of like your river. And you've got 3 sides of fence. Okay, so we're just going to label it this kind of like we did the last problem. X and X will be the height of the rectangle, Y will be the length. Okay, so your variables are just going to be X is equal to the height, and Y is going to be equal to the length, like that. Okay, so drawing a picture is pretty helpful anytime you're doing these problems then. Okay, the objective function is always what you're going to do a derivative of, and it's what you're optimizing. So what did the problem say you were optimizing? Remember, optimizing means min or max. What did it say? You're maximizing the area, okay? So what you're optimizing is the area, and we're trying to find a max. Okay, so it's important when you read the problem to identify what it is that you're optimizing. And the word problem is going to be clear on that. It's going to say max, min, smallest, largest. Okay, so I'll ask you a question. How do you find the area of the rectangle that I drew? Is it any different than the last problem? No, it's still the same. It's still X times Y. An area is base times height or length times width. So what we get is you get X times Y, and then you have the area in terms of 2 variables. The reason I write A of X comma Y is because it's got 2 variables. And when you're working these problems out, you don't want them to have 2 variables, you want them to have 1 variable. okay? So now the next thing is there a secondary equation? So look at what I highlighted in yellow. It says there's 96 feet of fence available. How do you do the perimeter of those three sides? Just add them up. So if you add x, x, and y, what do you get? 2x plus y. Okay, so you get 2x plus y, and that's equal to 96. That's what that part of the problem said, is that you have 96 feet of fence. That's what you're doing, okay? So now what we're going to do is we got to get this down to one variable. So what we're going to do is you decide which variable you solve this for. I'm just going to keep solving it for y because it's easier. So what I'm going to do is subtract 2x from both sides. You can do this in your head if you want to. Then you get y equals 96 minus 2x. Okay. Now, what do I do with 96 minus 2x? Where does that go? Into the x times y, in for the variable y. So it's going to go in there. Okay? So what you're trying to do is just get this down to one variable. So you have x times 96 minus 2x. Now that area is in terms of one variable. Okay, and that's what you're always trying to do. And once you get that objective function, then it's not too hard to finish up. Okay, so we're going to have a of x equals 96x minus 2x to the second. So that will be your objective function on that. Then we'll go ahead and finish that up. So that's the whole key. From here, what you're going to do is critical points in a sign chart, and then I'll talk about kind of constraints, and then I'm going to have you all finish this problem and see if you can do this, okay, before we take a break. Okay, so constraints on this. Well, here's the idea on this problem, is the biggest that this could be is 96, because you have 96 feet of fence available. So basically that value of y has to be between 0 and 96. If you just used up all 96 feet on the length, then you wouldn't have a width, right? So basically that value of y is going to fall somewhere between 0 and 96. Okay, constraints on the problem. I don't ever ask you for the constraints of a problem, but it's good to kind of reason that out. You realize once you get beyond 96, well, you've used up all your fence. That's all that is. Okay, so I'm going to have you all finish the problem. You need to go ahead and find your critical values, set the derivative equal to 0, make a sign chart, do a graph on your calculator of the objective function, and then you get your answer put together and everything. Okay, so let's go ahead and see if you can finish that up for a few minutes here. All right, what you should have got, of course, was your derivative, 96 minus 4x. You set that equal to 0. You get 24. When you make your sign chart, you should have got increasing and decreasing, so you know that's a max. Okay, using a test point like I used 1 and 25 to plug into the first derivative. Now on the graph, what I'm going to have on the graph is you're graphing the original function, which is 96x minus x squared. I went ahead and just did this viewing window right here. And when you do that, all you're trying to do with your graph is just verify that 24 is going to provide the max. So if I trace it 24, that does show that that's equal to the max. Okay, so on a graph, what you want to make sure that you just kind of for your own record, you're graphing 96x minus 2x squared, going 0 to 50, and then we're going 0 to 1500. You didn't have to do exactly this way. That would be one logical way to do that like that. So now what you're doing to wrap up the problem is what we found was 24, we had 24 and 24 there. Now remember, the perimeter is supposed to add up to 96, okay? So what you were given in the problem was you were given 2x plus y was equal to 96. So now all you got to do is plug the 24 in. So you do 2 times 24 plus y equals 96. You can do this almost in your head, I think. So you get 48 plus y equals 96. Get y equals 96 minus 48, which is 48. So that means the other dimension is 48. This time it's not a square like the last problem. So what you would end up getting on this just is 28. It would be 24 feet by 48 feet, like that. And then what you'd have to do is do the area. So the area is what comes out on your calculator. And if you do the area, you're just going to do 24 times 48 anyway, because it's length times width. And then that'll give you what that maximum area is. So we just do the length times width to get what that is, and that's what's coming out on the calculator. That's 1152. So you'd have 1152 square feet would be your answer to that problem then for the maximum area. So the big thing on the problem that you'll find is getting the objective function. If you get the objective function, I don't think you'll have much trouble because everybody got the 24 for their critical number and then the sign chart. The graphing is optional. You don't have to do graphing on these problems, but it's good to see how to check and verify your answer. That's why I'm spending a little bit of time doing that then. Okay, any questions on that or how I got the final answer or anything? Okay, all right, yep. Yeah, the area would just be the 24 times 48. The dimensions of the rectangle are 24 and 48. That's what makes that area a maximum. Okay. Yep. Okay, everybody okay? All right, let's go ahead and do a 10-minute break here then. Example 4. All right, a little bit different situation on this one. So this one, you're making a box out of a flat sheet of rectangle. And the box is going to be made out of this material. So it's 12 by 16. So the idea with this is what you're going to do is you're going to cut out these squares out of the corner. And then what you'll have is you'll be able, after you take a pair of scissors or whatever and cut out those squares, you'll be able to fold the flaps up and make a box that doesn't have a top. So the box is going to kind of look like what I've showed here. So there's all kinds of ways to draw this box. I mean, you could make the squares real small. And if you made the squares real small, the box would be real small, like kind of like a chocolate box, right? You know, that doesn't hold a lot. If the squares are a lot bigger, then the box is going to be taller, so it'll probably hold more. But there's only one way to make that so that it has the maximum volume. So what you're doing is you're maximizing the volume. Okay, so here's kind of what I want you to do on this diagram that I drew for you. First of all, you want to label this right here. This side right here, according to the problem, started off 16 inches. So you want to label that like that. And then this other side right here, that started off 12 inches like that. So just to kind of get a good picture of how this goes then. So what you're doing is you're chopping off these x's. This basically, on each of these dimensions right here, you're going to get this new dimension right here. So this started 12. When you chopped off two x's, you're going to get what's left. So this is going to be 12 minus 2x, okay, because you're taking out the two x's, okay? So you start with 12, then it goes down 2x. Okay, same thing happens with this side. You start 16, but then you chop off those two x's at the ends, and then this thing right here becomes 16 minus 2x. Okay, so that's the first thing that you got to understand is you start 16, then you chop off the two x's. You start 12, chop off the two x's. So in this diagram here, in this box that I drew, label this like this. This side right here, the longer side is going to be 16 minus 2x. The shorter side is going to be 12 minus 2x. What's the height going to be? How tall is that going to be? No idea? X, exactly. There you go. It's got to be X because that's what you folded up. Okay, you chopped off X. This right here becomes the height when you fold it up. Okay, so that's kind of the setup of the problem. And the variables are just going to be the dimension of the squares you cut out. Okay, what am I optimizing in this problem? What does the problem say? Volume. Okay, the volume, we're going to figure out what makes the volume a maximum on this. Okay, all right. Now, the objective function, we have to find the volume. Okay, you guys know the formula for the volume of a box? Yeah, length times width times height. Okay, so it's length times width times height. Okay, so the length is going to be 16 minus 2x. The height is going to be 12 minus 2x. And then the height is going to be x like that. Okay, so let's see. So we only have one variable. So what we have is this is our objective function. This is what we're going to be doing the derivative of and doing critical values and all that kind of stuff. So that is your objective function right there. Okay. Okay, so we got that. Now, reduce to one variable, well, not necessary, okay? We don't have to do that. So in this problem, our objective function only has one variable, okay? So does everybody understand that objective function, the length times width times height, okay? Okay. All right, so we're going to go down to kind of talking about constraints here. So here's kind of what happens on this problem. You start with 16 by 12, like that. So what's going to happen on this is the biggest thing that you could possibly get, if you folded this over, you couldn't go beyond 6 inches. Okay, so if you take like a square 6 by 6, there's no way you'll be able to make a box once it's bigger than 6. Okay, so what we end up getting is x has to be between 6 and 0. Okay, it's because you can't chop bigger than 6 if one of the sides starts 12 anyway. Okay, so now what we're going to do is going to do the critical numbers. So what we're going to need to do is we have to do the derivative of this objective function, and the easiest way to do this is to multiply this thing out. You don't want to use a product rule or any of that. We're just going to multiply this thing out, okay? So what I'm going to do is I'm going to FOIL this part right here. It's way easier to just FOIL and multiply this out, then the derivative will be really easy. Okay, so I'm going to do just kind of FOIL that. So I've got 16 times 12 is going to be 192. Then I've got the outside term, 16 times 2 would be minus 32x. Inside term would be minus 24x. And then the last term would be positive 4x squared like that. Okay, I've got like terms, so I'll have 192 minus 56x plus 4x squared times x like that. So what I did is I just FOILed that out. Now we're going to go ahead and just distribute that x through. So we're going to have 192x and then minus 56x to the second and then plus 4x to the third like that. So this is our objective function all multiplied out. Okay, any questions so far? Okay, all right, tell me what the derivative is, just in your head. Say something.
192 minus 112 plus 12x squared.
There you go. Okay, so easy derivative. See, it was a lot easier to just multiply the thing out. And then you can do power rule stuff like that. Okay, what I'm going to do is set that equal to 0. And I'm going to write this like this. I'm going to kind of put it in this order because what happens in this problem is it may not factor. Those are big numbers, and if it's a quadratic equation, then the best thing to do is to just plug this in the quadratic formula, which is what I'm going to do. So I'm going to write down the quadratic formula over at the side of the paper here. You don't have to write that down if you don't want to. But what we need to do is just use our calculator and do the quadratic formula on this. So we've got A is 12, B is negative 112, then we got C equals 192. So we're just going to plug it in the formula. All you need to do is just plug it in the formula, then we'll do the calculator together. So we'll have 4AC right there. There you go. Thank you. Okay, so we have negative B, so that'll be negative 112, plus or minus the square root of B squared. So again, B is negative 112 squared. 4 times A is 12, C is 192, and that's all over 2A like that. Okay, now what I'm going to do on here is we're going to do this on the calculator. So what I'm going to do is I'm going to just type in what's under the radical. We call that a discriminant. So I'm just going to do exactly what that part tells me to do. So I'm going to do negative 112 to the second minus 4 times 12 times 192. And that'll give me 3,328. And then 2 times 12 is going to be 24 like that. Okay, now we're going to just do this on the calculator. You get 2 answers out of this, and it's important that you go ahead and get your 2 answers. So you can kind of watch how I do this on the calculator. I'm going to do the numerator, 112, plus the square root of 3328. I'm just going to get that, and then I'm going to divide that by 24. Okay, so I end up getting 2 answers. I'm going to get about 7.07, and then there's another answer. I just got to do the minus. So what I do now is I do 112 minus the square root of 3328, and then I divide that by 24. Okay, so I get another answer I get is about 2.26, and these things are in inches like that. Okay, so that's quadratic formula. Any question about quadratic formula? Generally, students okay with that. I just make sure that you can put that in the calculator okay. Now, one of those answers makes sense and one of them does not make sense. Remember, you started off with 16 by 12. Which of those 2 numbers doesn't make sense? The 7. It's too big. Okay, remember, you can't chop off. If you're going to make a square, the biggest square you can possibly make is 6 by 6. So that's too big. Okay, so we have that. So what we'll do next is we only have one thing here. So when we do a sign chart, we're just going to start with x equals 0. You know, we don't analyze any negative numbers. We're making a box, and boxes don't have negative dimensions to them. So we have the x equals 2.26. And then here we'll just go all the way to 6. We don't need to go beyond 6 because the problem doesn't make any sense once you're past 6. Okay, so what we'll do is we're going to plug test points in. And I'm not going to show the work on this. You would just plug into your derivative. So you would do 192 minus 112 times 1 plus 12 times 1 to the second. That would be a positive, so that tells you the function increases. You could pick a test point here. We'll use 3. So if I do 192 minus 112 times 3 plus 12 times 3 to the second, that's a negative, so that means we decrease. Okay? So I'm just not going to take the time to show the arithmetic on that because you can do that fine. But anyway, is that a maximum? If the graph increases, then decreases, does that look like a maximum to you? Yeah, okay, the graph increases, hits a max, then it decreases. Okay, so mainly what I want to see on your sign chart is just the plus minus and the 0, 2.26, and 6 like that. Okay, so that's the problem on that one. Now what we'll do is we'll just check this graphically and see if this is right. One of the reasons I like to do check graphically is because I don't mind, like on a test on some of these types of problems, if you do this graphically. I'll give you the choice to either do a sign chart or just check it graphically. It's kind of your choice on how you do this. So what you want to do is you want to put in the function that we took the derivative of. Now I'm going to go all the way back here, and instead of putting the multiplied form out, I'm going to put in 16 minus 2x, and then times 12 minus 2x. And the reason I'm doing this is because if I made a mistake when I multiplied that out, then I really wouldn't be checking the problem. Okay, so I'm just going to have you put in your graphing calculator like this, and then I'll give you a window to put together on this problem too. Okay, so you want to go ahead and just get that in. And for the window, we're just gonna graph again 16 minus 2x, 12 minus 2x times x. And then the window will go like this. We'll go 0 to 6 on the x-axis. And then for the y, let's see, we'll just let's do something like this. So we'll go 0 to 6 by a scale of 1, y minimum 0, then we'll go all the way up to 200 on this one, and then scale that by 50. Oops. And then I'm just going to have you just sketch out the graph that's going to come out on here anyway, okay? And really all I want to see is 3 points, the beginning, the end, and that maximum on that. So here's basically what happens on your graph. You need to just write a really rough sketch of this. You're just kind of going up to 6, that's sufficient. Then you're going up to 200, that's sufficient right there. And then you're going to have these 2 points. You'll have like 6, 0, you'll have the point 0, 0. And then if you trace out that 2.26, where that critical value was, then you would get this point 2.26, 194.07, like that, if you round that off, okay? All right, so that's the graph. You can pretty well tell that that gives you a maximum. You can tell that's pretty well verifying that then. Okay, all right, any question on this one? Okay, now what we need to do now is just kind of put this together to get our answer. So it's going to go like this. We're going to do the length. The length is 12 minus 2x. So we do 12 minus 2 times 2.26. And that will give what the length of the box is that we're making. So I'll just kind of do that on the calculator here. So 12 minus 2 times parentheses 2 plus 2, 6. That will give 7.48 inches. And then the width was, or hold on, this was the width. It doesn't matter which is which. The length is usually the longer side, so that was 16 minus 2x. So we'll do 16 minus 2 times 2.26. That'll give the length. Okay, and that will give 1148 inches, and then the height was just x, so the height is just equal to 2.26 inches. So your dimensions, you can just say 2.26 inches by 7.48 inches by 11.48 inches. So that would be the dimensions that would maximize the volume of that box. Okay, that's how that gets put together. Okay, all right, and then the last thing would be the volume. Okay, the easiest way to do the volume is do it on your calculator. The volume is length times width times height. So all we got to do is just do 2.26 inches times 7.48 inches by 11.48 inches, and then that'll give you that maximum volume. So I'll go ahead and put that on my calculator. And the calculator gives that answer to you anyway, and I'll show you where that is. So we get that times this. And this would be your answer to your volume would be about 194.07, and that would be cubic inches on this. Okay, so that would be how you get the whole thing put together. Now notice on your graph, like if you trace it 2.26, I mean, we graph the volume. Here's another way to get your volume. It's just trace it 2.26. There it is. It's 194.07 right there. So you don't have to do that necessarily. You can get that from the calculator. Okay? All right. Any problem with that? Okay. Everybody feel okay with what I did? I mean, the methodology of these problems is always the same. It's always getting an objective function, then doing critical numbers, sign chart, graph to verify that you're doing everything right. If you can get the objective function right, you're probably going to be okay. All right, that's what I find. Okay, we'll do a business example, and then we're going to try to finish up with kind of putting that last example together. So this one, we've worked with profit quite a bit. So this one, you're given a cost function, you're given a price demand function, and you're given this domain from 0 to 25,000. Just says you're selling calculators. X is the number of calculators. So we're going to find the production level that maximizes the profit and the maximum profit. Okay, tell me what the formula for profit is. Revenue minus cost. How about revenue? X times P. So you want to write those two formulas down. Our objective function is just simply going to be the profit function. So to begin with, we have to get the revenue. The revenue is X times P. And notice I gave you P is the price demand function. So you do X times 14 minus X over 4,000. So that would end up giving 14X minus X to the second over 4,000 for your revenue function. Okay, so we got that, and you all have done that before. We've learned that formula before. Now we're going to do the profit. So the profit, you're going to take the revenue, which is 14x minus x squared over 4,000 minus the cost function, like this, and collect your like terms and make sure you don't make any mistakes with your negatives and everything. So we're going to have 14x minus x squared over 4,000 minus 8,000 minus 5x, and then we can put the like terms together. So I'll write in the answer blank, we get negative x squared over 4,000, and then 14 minus 5 is going to be plus 9x minus 8,000, like that. Okay, so that's the profit, that's your revenue minus cost. That's what we're going to work with and kind of get everything put together with. Okay, anybody have a question about that? Okay, now what I want you all to go ahead and do is I want you to find the critical numbers and the sign chart, and then give you a few minutes to try to put together a graph. So let's go ahead and just kind of work on that for a few minutes here and see if you can get your critical number and your sign chart put together on that. Okay, so let's go ahead and see if you can get that okay. The derivative on that's pretty simple. And that 4,000 is a constant. So, the derivative on this, sometimes students make some mistakes on for some reason because of that 4,000. We know the derivative of negative x squared is negative 2x, but that 4,000 just writes down. And then we know the derivative of 9x is 9, and then that derivative of 8,000 is 0. So what I'm going to go ahead and do is I'm going to simplify this, and then I'll let you solve the equation and kind of put that together. So you can reduce that down to this. Now go ahead and set that equal to 0, then just do your sign chart. That's all I want you to do is just do those two things. Just take a minute to get your critical number and put together your sign chart. And I'll do the graphing with you together. I'll do that with you. Okay, so that'll wrap that up, and then I'll finish that up. You can finish that up if you want to. It's not that hard to do that. Okay? All right, don't forget you need to turn in your written assignment 7. We only have one more after this one, so come up if you need help. I'll be here till 2 o'clock today, as usual.
Can I skip there's a wait for office hours to do the witness?
What?
Can I just get help with the witness on the
Yeah.
office hours?
Yeah.